tree. So you would say something like 100, and then you would have, it would be best if you keep these all aligned. So you have a cell that works. Sometimes it's easier said than done, but I'd like for you guys to be able to work quickly with this. So if we have this, what we would say is we'd say this value equals the 100 times, and you'd have a cell for your upstate, but I'm just showing you an example. So we have equals the previous value, and you could say times the upstate, or you could say the original value times the upstate squared, either way that you want. And then you would have the same thing for your call values, but remember your call values you have to work your way back, so you could set this up as the max. And again, the reason that I'm setting this up is that sometimes these will change, so you would say the max of st minus x, and I don't have an x here, so I'm just going to use this, or 0. And then as you drag down, you would have the right number. It's important to make sure that your spaces are important. So as you drag down, you could say that this one is, let's call this one 100, and let's just say there were one other one in here, so let's say this is 150, 100, and let's just say this is, now obviously by me putting another one in here, I'm assuming that there's another period. You can't get a value in between these. And let's just say this is 50, but I just wanted to show you what the dragging would do. Hopefully it works. There you go. Now these don't mean anything because they're not in line, but you would end up with the call values in the ending period, and then you would discount back. So you would use your probabilities, you would take these two and come up with a value here, you would take these two and come up with a value here, and work your way back. It'll be clearer once we have 4 or 5 periods that we're working with, but it's the same process each time. Find the expected value, discount back. The reason I explained it so much is because once you start looking at these slides, and I'm trying to go over them, these just look like gibberish, right? The call in the upstate is equal to the probability of the call in the upstate plus 1 minus the probability of the call in the downstate divided by 1 plus the risk free rate. All that really means is if you're looking for this value, you take the weighted average, or the probability weighted average of these two, and discount back a period. When you're looking for the call in the downstate, you take the probability weighted average of the two possibilities and discount back. When you're looking for Z0, you do the same thing. Pretty simple. If you jump to conclusions and you feel like getting a little bit aggressive with these, right? The probability squared times the call in the upstate, that's what I did when I said 0.4 times 0.4 equals 0.16, times that 300, plus 2 times the probability that you moved up, down, that's because there were 2 paths, times the value in the middle, plus 1 minus the probability, that was 0.6 squared, times the value in the downstate. Now what happened was this was 0 and this was 0, so all you had to do was this. It's convenient if you have zeros just to jump to conclusions, because then you don't have to discount, discount, discount. We just did this. We know that it's 3966, right? Assume you have 2 periods, same model, moves up, up, we get to 400. So we just did this. All right, so even if we have 3 terminal values, and again, if you have 2 states, if you have 2 periods, 1, 2, you have 3 states. If you have 3 periods, you have 4 states. 4 periods, 5 states. Now, if we add more and more periods, sometimes we can get to something that approaches feasibility. assume that the stock moves up by 10 or down by 10. Now, there's a big mistake in this up by 10 or down by 10, is because as the price changes, right, it's much more common for a $200 stock to move up by $10 than it is for a $50 stock to move down by $10. But let's just assume that this is the case, and we end up with 10 periods. In both cases, the probability of the up movement is equal to the probability of the down movement, so we have a 0.5 times 0.5. What we would end up with are these probabilities. So we can see now with 10 states, 10 periods, we end up with 11 states of the world. The probability that it goes up, 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 same type of thing, flipping ahead 10 times in a row, you end up with a 0.1% probability. Same state down, you can see the much more heavily weighted. There's 65% happen in these three cases, right around the middle. And if we expand out, 86% or 87% happen between 60 and 140. So these much more kind of what we call close to the money prices, right, happen with a lot more frequency. That's why when you look at something way out of the money, the price of it is very small. In puts, it has to be way below the money. Most of the time, most of the action happens right around these more heavily probability weighted prices. Again, if we were to take this out another period, 0, we can't go to a negative stock price, right? But we can keep going up and up and up, that's fine. So we have to come up with something that even resembles this a little bit more. Again, when we're doing a binomial and we have equal weights, what we approach is this kind of, the most average price is the current price. This goes back to that martingale theory. Our best expectation of the future price is our current price, and then each price, the farther out it gets, is a little bit less likely. As we add even more periods, as we change it from 10 to 60, and we decrease the movements to only $1,